Hi, we are group one for CSE 535, and this is our final project for the CGM prediction. I'll start with the common filter. We went in and we predicted what the CGM data would be based on previous states, and we graphed that data on a graph versus the actual CGM data. So as you can see, the common filter was pretty accurate with predicting, the next CGM data. And from that, we were able to kind of predict when meals were going to come based on how close the common filter was to the actual CGM data. So we go in and we detect the meals, and then we plot that on a graph as well. So this is an example of a part of the meal prediction. These red lines are where we're saying meals are being predicted, basically. And as you can see, they closely line up with the bolus data, which we're considering ground truth, and they also coincide with the peaks in the CGM data, which are where meals are typically found.
So for our auto-regression-based modeling implementation, we first started using Jupyter Notebook for it. And to start off, we imported a bunch of libraries from stats models and sklearn to basically calculate the algorithm using Surima. So to first start off, we still load in the data just as usual, but then we had to explicitly, for just easier reference, we created a data frame for both test data and the training data. And then we're just plotting out the points here. You can see that there's a left skewed distribution for the axis subplot. But then as we progress down, we do a add fuller result or add fuller method to determine whether the statistic is stationary or the data set is stationary or not. And we determined that the data is stationary because the p-value is less than 0.05, where as of right now, it's just 0.0. And as we progress through, we also plot the autoregression plot, which you can see is just based like this. And then later on, we actually start progressing into using Surimax to develop the autoregression model. So we implement our training data in, and we basically put in our training data through the Surimax, and this is our result. As you can see, it's very skewed. And just from looking at the normal QQ graph alone, you can see that it doesn't follow normal distribution just from that result there. And then basically, right after, we have to calculate the prediction part, which is when we implement our test data in, and we get an R-squared scored of negative 0.14, which is not, it's basically showcasing that our data or our model is not good at covering the majority of our data set, as it only covers 14.8%. So maybe that model that we have just built and trained is not a good model to use. So in the future, we can normalize the data to increase the accuracy, but also we can also standardize the data set to basically minimize the effects of outliers on the lower or inner quartiles of the data.
All right, I did the R&R meal detection. So I bring in the CGM data, I split it 70-30 to train test. I then create my features and labels. Here, it grabs all the features, puts them into a NumPy array as well as the labels. I reshape the features and have it as an input for the long short-term memory, part of the sequential RNN model. I then add the density, compile it, and I start a training time so I could get a final time of how long it took, get the early stopping value, history and loss, and then it compiles it and it saves the model and then ends the training time. Then prints the training time for you and grabs the predictions and returns them. This is all done here, where then it detects the meals, threshold of 5, and detects the meals based on the predicted RNNs. It then outputs that to the graph as well. Here you could see the features, the labels, the epochs, and normally would have 100, but as you can see, it took 167 seconds for just two. I didn't, an hour long wait, just was a little extensive. All right, and then here we have the graph